So if we drag this across, we're doing the same binomial probability calculation for these different values of x, 0 through 5. And so each of these are, so this is for x equals 0, x equals 1, 2, 3, 4, and 5. So we can see which one of these choices have these, and since the answer is already marked here, we can check if C is correct. So x equals 0, probability is 0.328, so it's slightly more than 0.3, so that's correct. And then for x equals 1, that's slightly more than 0.4, which is correct, 0.41. And x equals 2, the third bar is about 0.2, right there. And the next one is 0.05, so that's about half of 0.1, so which is right there. And then there's 0.01, which is down to very close to 0, and this is just kind of too small, which is very close to 0. So that's the right distribution. And now we need to find the mean. The mean is n times p, so that would be just n multiplied by p, which is just 1. And the standard deviation is, as you remember, that would be the square root of n times p times q. So that's what it is, and we can use the Excel from the SQRT. That's the square root of n times p times q. So the mean is 1, and the square root, the standard deviation is about 0.89. So mean is 1.894. Alright, that's number 4. So here's number 5. Okay, so in number 5, we have a normal distribution with mean 80 and standard deviation 5. So find the area under the normal curve and above the interval 70 to 87 on the horizontal axis. So this kind of illustrates what we need to do. So we need to calculate the z-scores for these interval boundaries. And for this z-score, for example, what this table gives is, as it says here, the area under the standard normal curve from 0 to z. So for this z-score, when you look it up on this table, the number the table gives you is this area from 0 to that z. So keep that in mind. So now look at this interval. It's 70 to 87 and 70 to 87. So for I'm gonna put x1 equals 70 and x2 equals 87. So the z1 is the mean is 80, so it's 70 minus 80, and I need to put this in parentheses, 70 minus 80 divided by 5, because the way you calculate the z-score is x minus mu, the mean, divided by standard deviation 5. So 70 minus 80, which is negative 10, divided by 5, which is negative 2. So we figure out z2 the same way, which is 87 this time, 87 minus 80, and make sure that is inside parentheses, divided by 5, and that's going to give me 1.4. So remember, the z-scores are negative 2 and 1.4. So 1.4 is here and negative 2 is back here somewhere. So let's figure out 1.4 first. So z 1.4 is here, and since after the 0.4 we have the exact, there's no other decimal, so the value is 0.4192. So write that down, 0.4192. 4192, that's the area under the curve. So imagine this is 1.4, so this is this shaded area. Now -2 is here, so then I need to figure out this area between -2 and 0, which is this area. And that area is, since this is a symmetric bell curve, then this table doesn't give the negative values. So that's why we're looking at the symmetric value instead of z equals 2. If I look at -2, if I look at z equals 2 and check out this area, that would be the same value because it's symmetric. So looking at z equals 2.0, which is 0.4772. 0.4772. And the total area for this interval, which is 70 to 87, would be the addition of these two. So if you add these two up, you get 0.8964. So that's our answer. 0.8964 is the area. That's number 5. Alright, number 6. Alright, number 6 is very similar to one of the previous questions we did. So watch carefully how I build this. So we have nx pq. N is here 7. X is going to be 0 through 7. So 1, 2, 3, 4, 5, 6, 7. So n is always 7. P and Q are the same. So P is 0.3, so 0.3, and Q is 0.7, 0.7. So those are, we can figure it out from this formula. So P and Q never change, so copy those across. So now the probability Px is given in this formula. It's equals combination, so combin, parentheses, n comma x, close parentheses, times p to the power x times q to the power, parentheses, n minus x. Enter. So this is the probability for x equals 0. If I just drag this across, I'm having x, I'll calculate the exact same probability for values of x, 1, 2, 3, all the way up to 7. So there's my probability distribution. So for x equals 0, the probability is 0.82. 0.82 is it's slightly less than 0.1. So not all the way down, but slightly less than 0.1. So this is correct. And then for the next bar should be x equals 1, which is the probability is 0.24. So that's almost like a quarter, almost 25. 0.25. See, 0.2 is here, and that's like halfway between 0.2 and 0.3, which is right. And then the next one is 0.31 or 32. That's slightly above 0.3. That's right. And then the next one is 0.22, slightly above 0.2, which is right again. And then 0.1 exactly across here. And then the last one, no, not the last one, second to last is 0.003, very small, close to 0. And the last one is even smaller than that. So that's going to be barely zero. So this is the correct distribution table because we figured out each value in the distribution. And then we need to find the mean. The mean is simple. The mean is n times p, which is 2.1. That's how we figure it. And the standard deviation is square root of n times p times q, close parentheses. So that's 1.212. There it is. So that's 6. Number 7. So number 7 is another binomial distribution probability problem. And we can actually use this. So let me just clear this from the previous example. What we need to do is the probability of, okay, first off, here n is 7, so there it is. X is 3, so I'm going to put 3 here. And P is 0.4, so not 0.3, but 0.4. And Q is always 1 minus P, so that's going to be 0.6. And voila, that's the probability, 0.290. And again, you can see, since we crafted the formula already, that's combination of 7, 3 times 0.4 to the power 3 times 0.6 to the power, the difference, 0.6 to the power 4. And that gives you 0.29. Let's look at number 8. A fair die is rolled 4 times. What is the probability of obtaining no 6s? Okay, no 6s. So when you roll a die, the probability of rolling any number is 1 over 6. So equals 1 over 6. That's the probability. So when you roll it 4 times, you don't want any 6s. It could be anything but 6. So why don't we calculate the probability of rolling all 4 6s, and then subtract it. Actually, I'm not sure if that would work. Just hold on a second. Okay, forget what I just said. So just think really simple. You're rolling a die, and any outcome is fine except 6. So the probability of rolling a 1 or 2 or 3 or 4 or 5 would be just 5 out of 6. So our probability is 5 out of 6, because we want anything but 6, and that's 5 over 6. And you roll this 4 times, and every time the probability of not getting a 6, so anything but 6, is always 5 over 6. So then the answer would be 5 over 6 times 5 over 6 times 5 over 6 times 5 over 6. So that's basically 5 over 6. This is the decimal value of that, to the power 4. And that will be 0.4822. Round to 3 decimal places. Let's do that. It's not working. Okay, there. So 0.482. Okay, number 9. Let's read the question. Okay, number 9. The rule of thumb here is, this has to do with the central limit theorem. Which means that if the sample mean is large enough, the sample size is large enough for a binomial distribution, then it can be approximated to a normal distribution. And here's how we check. We check the mean as well as the variance of the binomial distribution, and if each one is greater than or equal to 10, then we can approximate it to a normal distribution. So let's check. We don't need these. So the n is 24 here, and p is 0.9, which means q would be 0.1, so it's 1 minus p. And this is mean, and this is variance. Mean is n times p, so 24 times 0.9, which is 21.9, and that's actually greater than 10, so that's true. The variance is n times p times q, which gives us this, and on